Here is Scope animating from the time records that we extracted from the video. So you can see the cursor sweeping through the time records up here and displaying the deflection of the bench grinder at each moment in time. We call that a time-based ODS. There are 10,000. Here, if we look in the spreadsheet, there are over 10,000 measurements animating 5,000 points, a grid of points behind the graphics of the video. And you can see here a lot of motion of the polishing wheel on the left, and you can also see some motion of the grinding wheel on the right. And if you look real hard, you can see some motion of the base also. Well, we can use Scope to change the amplitude. So let me click up here under the Animate menu, and I'm just going to increase the amplitude of the ODS animation. So now we can see clearly the base is moving around and the two wheels are moving with more motion. This is showing us essentially a mode of vibration of the entire machine that's dominating the ODS. This is what we call rigid body mode of the machine, and here we're seeing some flexible motion of both of the wheels, a lot of motion over here because of the soft material, but what looks like a mode shape here of the grinding wheel. Now, if we click down here below, we're looking at the spectrum now of these time records, and this is an envelope of all the spectra. If I look over here in the spreadsheet of the properties, I've got 10,000 spectra, one for each point in the X and Y direction, and then one more additional spectrum, which is the envelope that we're animating from right here. And you can see the orders of the machine are clearly displayed in the envelope. Let's crank this amplitude up a little bit. So I'm going to go back here to animate and increase the amplitude of this spectra. And you can see pretty much the same thing we saw from the time records, although this is being animated with sinusoidal response. So you can see that up here under the Animate menu. It's called Sine Dwell. So we're simply animating, and now you can see a clear resonance of the grinding wheel and some wild motion here of the polishing wheel. And the base is moving around. Let's move to let's go to the second order. Now the base is no longer moving, but we have a different mode of vibration of the grinding wheel. So that mode is now dominating the ODS. And of course we have the motion of this polishing wheel also, and what looks like almost a mode of vibration of that soft material. Let's go to the next order, the third order. A more complicated mode shape of the grinding wheel is now dominating the ODS, and a more complicated motion over here. Notice also that the base is no longer moving, so the wheels themselves are dominating these higher frequency orders of the machine. Here's a higher order. This is what, the fourth order, and you can see now the two sides of the grinding wheel are moving differently from one another. And let's just look at the fifth order here, the final one. Again, none of these have any participation from the machine itself, but the ODSs are being dominated by modes of the wheels. And that is a validation of one of the laws of modal analysis, and that is that all vibration is a summation of mode shapes. So down here, again, at the operating speed, we have a mode shape, which we call a rigid body mode of the entire machine. combined with some participation of the modes of the two grinding wheels. Again, I'll just put it back here to the second order, and now there is no participation of the machine, the rigid body motion, but there's still a mode shape of a different mode shape of the grinding wheels in both cases. Now there's another peak down here below the running speed. Let's go down and take a look at that. Wow, here it is. It's a rigid body motion of the entire machine, and it is actually bouncing on some foam rubber. Because the machine was moving around so much on the tabletop, because of its high vibration, we put it on some foam rubber. And so this is really what we would call soft foot. The frequency is about 1,000 RPM, less than the running speed, but there is an ODS there that's being dominated by essentially rigid body motion of the entire machine bouncing on the foam rubber. So the frequency is influenced by the stiffness of the foam rubber and the mass of the machine itself. Very interesting result that the video captured for us. Now we're going to do one more thing, and that is actually put some numerical values right on the model itself, which then could be recorded as part of the video. How do we do that? I have a couple hotkeys up here. One is called select points. So that's going to stop the animation and allow us to select some points on the surface behind the video. And the other one is magnitude and phase. So we're going to display the magnitude and phase at those selected points. I'm going to click on the first one, and you can see that what I've got here now is a transparent view of the graphics and the points behind. Down here is a little floating dialog called click select. That's part of the click select command. I'm going to move over here and click on the multi-select. And I'll just pick one of these wild points here, and we'll look at its deflection. And then we're going to go ahead and differentiate this data and look at the motion in units of velocity. And then I'll pick a point down here on the base that's not moving very much. So there's 3 points. I'll close the click select box. And if we look up here in the spreadsheet, those points have been selected. If I double click on this column here that says display magnitude and phase, I'll say yes. So now those points have been selected and we're displaying the magnitude and phase on them. So you can see a little box here next to each of those points showing the magnitude and phase. Most of the motion here is still 1/100th of an inch, not very much in terms of scale data, and then very little motion on the base here and less motion on the grinding wheel. Let me press the other hotkey and that will resume the animation. So there we are, and we're still animating from the spectrum data down here. So this is the motion at the running speed. And I can click back up here and I can display the motion also, that you can see that it's moving around quite a bit. So I'd have to switch back and stop or pause the animation to actually see those values. But again, you see the same thing, very little motion on the base, on the grinding wheel, and most of the motion is over here on the polishing wheel. Okay, well let's go back and look at the inches per second of vibration, because machinery people are familiar with that, and rule of thumb is if a machine is vibrating over an inch per second, that's excessive vibration. Again, when it's a resonance. So let's do that, and that's a simple command in ME Scope that we'll execute out of the Tools menu. differentiate. So I'm going to differentiate the data. There it is. It's been differentiated. So now at the running speed, we've got somewhere on this model is 21 inches per second. Well, that's clearly got to be over there on the soft material of the polishing wheel. But if I look over here on the grinding wheel, its motion is a little over 1 inch per second. For a small machine like this, that's very, very realistic. And then down here on the base, hardly any motion at all. Well, 0.2 of an inch per second. And then over here on the wheel, if I just look at the value that I chose on that one point on the wheel, it's 6.3 inches per second. So what we got here was some realistic data off of a video, which we couldn't have gotten in any other way with any type of a contacting sensor. We could have used a laser system perhaps, but a lot more expensive and so forth than simply recording a video with a cell phone.